In this video, we'll be looking at linear quadratic systems. And this is a system that involves a line and a parabola, and we are looking for the point of intersection. So visually, it might look something like this. We might have a parabola that's opening up, and we have a line that's going upwards. This is a system, and the solution to the system is the point of intersection, which in this case, we have 2 points of intersection. So we can actually have 2 points of intersection. We could have 1 point of intersection, and that would be if our line just touched 1 point, or we can have 0 points of intersection, and that would be if, let's say, our parabola is opening up like in this case, and our line is way below so that they don't actually meet. Now, in order for us to solve, like I said, we are going to use substitution, which means we're just going to set our two equations equal to each other and then solve the equation. And what we're going to be left with is a quadratic equation, which means we're going to bring everything to one side and then solve by either factoring or using the quadratic formula. So let's check out our first example. We have f at x equals x plus 13, and remember, this is just y equals x plus 13, and then our parabola is g of x equals x squared minus 3x plus 8, and again, this is the same as y equals x squared minus 3x plus 8. So just remember that that function notation represents the y. So now, because they're both equal to y, I can just replace y in the parabola with what y is equal to in my linear equation. So then I am substituting the line into the quadratic equation so that we're left with x plus 13 equals x squared minus 3x plus 8. And I know this is a quadratic equation because I see that x squared, and in order for us to solve the quadratic equation, we have to put it into standard form, which means we need to bring everything to the other side. So I'm going to bring x over, so that it's going to be minus x, and I'm going to bring the 13 over, and it's going to be minus 13. So I'm left with a 0 on the left, which was my goal. I still have x squared, and then negative 3x subtract x because of that opposite sign. We have minus 4x, and then 8 minus 13, and we have negative 5. Now, if you can factor this, go ahead, or when in doubt, use quadratic formula. But in this case, we can factor because it's a simple trinomial. We're looking for a product of negative 5 and a sum of negative 4, and our magic numbers are negative 5 and positive 1. So 0 is equal to x minus 5, x plus 1, and then we can branch out, set each bracket equal to 0, and solve for x. So for the first bracket, when I bring that negative 5 over, I'm going to have x equals 5, and for the other one, x equals negative 1. Now, this means that there are 2 points of intersection, and we do need the full coordinate, which means we're going to have to sub in 5 for x and negative 1 and for x to solve for the coordinate fully. So you can pick which equation you want to sub it into, the line or the parabola. You should get the same answer, and that's actually a good way to check your work to see if you've done it correctly. If I take 5 and I plug it into f at x and g of x, hopefully I should get the exact same value, and same for the negative 1. But I'm just going to plug it into the line because it's just easier. So I'm going to do f at 5, and that's going to equal 5 plus 13, which is 18. So that means our first coordinate for the point of intersection is 5, 18. And then I'll put negative 1 into f at x so that I have negative 1 plus 13, which is 12. So then that coordinate is negative 1, 12. And then those are my 2 points of intersection. And that's it. So now let's try the next one. F at x equals 3x squared plus 4x plus 4, and g of x equals 2x plus 6. Again, I'm just going to do a substitution here. I'm going to set my two equations equal to each other. So this part equals this part because they're both equal to y. So I'm just setting the y expressions equal to each other. So I have 3x squared plus 4x plus 4 equals 2x plus 6. And then once again, I'm going to bring everything to one side. So I'm going to bring the 2x over, and I'm going to end up subtracting it. And I'm going to bring the 6 over, and I'm going to subtract it again, switching the signs, so that I'm left with 3x squared plus 2x minus 2 equals 0. And then now we can try to find the magic numbers and try to do decomposition. So I'd be looking for two numbers that multiply to -6 for when I multiply 3 and -2, but adds up to 2. And we can't actually find that combination, so we have to do quadratic formula here. So x equals -b, so -2, plus or minus b squared, so 2 squared, minus 4a, which is 3, c, which is -2, and then all over 2 times our a value. And now we can clean it up. So when we clean it up, I'll leave the -2 as is, but under the square root, it will become 28, and then all over 6. Now we do have to use our radical knowledge here, because we know that 28 can get broken down into 4 and 7. So just a little side note here, 28 is the square root of 4 times the square root of 7, which means it's 2 root 7. So don't forget about your radical knowledge. So now we have -2 plus or minus 2 root 7 over 6. And then I noticed that all of the coefficients are constant. So the -2, the 2, and the 6, they're all divisible by 2. So I'm going to go ahead and do that to simplify it. And you can only simplify it if all 3 of those numbers have something in common. So I end up with -1 plus or minus square root of 7 divided by 3. So those are my two options for the x coordinates, one when we have addition and one when we have subtraction. So now we have to sub it into our equation, and we are going to keep it in exact form. And to make our life easier, of course, I am going to sub it into the line equation. So that is g of x. And I'm going to start with the positive version. So g at -1 plus root 7 over 3. And now I'm just going to write 2, and then instead of x, I'm going to write this entire thing, and then plus 6. And now when I simplify it, first thing I'm going to do is multiply my two numbers here, and I'm going to put the 2 over 1. So the 2 is going to get multiplied by the numerator, and the 1 times the 3. So that will simplify to -2 plus 2 root 7 over 3, because I am distributing that 2 in fully. And now with that 6, I don't want to just write plus 6 because I know I have to turn this into one nice fraction. So I need a common denominator. So this is 6 over 1 right now. So I'm going to multiply top and bottom by 3 to get the same denominator as my first fraction, which gives me 18 over 3. And now we can finish this off by just adding our constants. So I'm going to add the -2 with the positive 18. The radical, there's nothing I can do with it because there's no other like radical for me to combine it with. So -2 plus 18 is 16. So we have 16 plus 2 root 7 all over 3. So that's our first point of intersection. So I'm just going to write it, -1 plus root 7 over 3, comma, 16 plus 2 root 7 over 3. So there's number 1. And then we can do the same thing for the negative version. But the only thing that's going to change is that this is going to be subtraction throughout. So actually, the 16 will not be changing. The only difference is that it will be 16 subtract 2 root 7. And if you wanted to, you could have actually done this all at once. So I could have had plus or minus, plus or minus, plus or minus throughout. And you would notice that because there is no other radical that I'm ever going to combine it with, it won't change. So my second point of intersection is going to be -1 minus root 7 over 3, comma, 16 minus 2 root 7 over 3. And that's it for this one. So the actual quadratic formula and the substitution part is a very grade 10 skill. It's just your knowledge of simplifying radicals is the extra grade 11 twist. So here's our next linear quadratic system. So I want you to pause the video here and try it out on your own. I will tell you right now that you will only have one point of intersection, so don't be scared if that happens, but I want you to try it on your own and then come back to the video to check your work. All right, so first thing, I'm gonna set my equations equal to each other. So hopefully you wrote x plus 1 equals x squared plus 5x plus 5, or the other way around, doesn't matter. Bring everything over to the other side. So 0 equals x squared, and then 4x because 5x subtract x, and then plus 4 because again, 5 subtract 1. And now I'm going to factor this because it's a simple trinomial and there are two numbers that multiply to 4 and add up to 4. And both of those numbers are actually 2, which means this is actually a perfect square trinomial. So I'm going to have x plus 2 and x plus 2. So then when I branch out, both of my solutions are -2. So I don't actually have to write them out twice. So what this means is that you do still have two real solutions. They're just both -2. But you only have one real distinct solution. So there's only one point of intersection you will see, but technically there are still two real solutions. They're just both the exact same thing. So now I'm going to plug it into t of x. So t at -2 was -2 plus 1, which is -1. So your point of intersection is -2, -1. So I'll just write therefore, POY at -2, -1. And that's it for that one. And now let's try our last one. So once again, I want you to try to set this up on your own. And you might have to do quadratic formula for this one. And there will be something a little weird that happens, but that's okay, it's supposed to happen. So try it out, see what happens, then come back to the video to check your work. Okay, so we should have x minus 5 equals 3x squared plus 2x plus 3. Bring everything over so that we have 3x squared and then plus x because we're doing 2x minus x, and then plus 8 because we're doing 3 plus 5. And now you might ask two numbers that multiply to 24 and add up to 1, and that doesn't work. So I'm going to go to quadratic formula. So -b plus or minus b squared minus 4ac all over 2a. And now when I clean this up, under my square root, I actually get -95 and then all over 6. And we know that we can't square root a negative. So we can't square root negative, and that just means there's no solution, so there's no point of intersection. Therefore, no real solution, meaning no point of intersection. All right, so for these four examples, we actually solved for the point of intersection because it said solve the system or determine where the functions intersect. But there are types of questions where you might just be asked about the number of points of intersections or the number of solutions. So in that scenario, we use the discriminant, and that just saves us time from actually trying to fully solve. So the discriminant is the part that is under the square root. So it is this b squared minus 4ac, because if you look at the previous questions, you will notice that when we tried to square root a negative number, there was no solution. But in part B, where we tried to square root the positive number, we had two solutions. So for the discriminant, if you put your quadratic equation in standard form into the b squared minus 4ac part, if your discriminant is greater than 0, so discriminant is positive, then you will have two real distinct solutions. if you put into the discriminant and you get a number less than 0, so a negative number, you have 0 real solutions, which also means you have 0 x-intercepts. And likewise, when the discriminant is positive, you have 2 x-intercepts. But you can also have the option where the discriminant is equal to 0. So if you're doing your quadratic formula and you have plus or minus the square root of 0, you're technically adding and subtracting 0. Adding or subtracting 0 to a number gives the exact same number. So in that scenario, you will only have one distinct solution. So there's still 2 real solutions, but only one distinct 0. So I'm just going to reword this in a few different ways. It is 2 real solutions, but it's only one distinct solution, which visually means you have only one x-intercept or 1 0. Whereas when the discriminant was positive, you had 2 distinct zeros that you could see. Or if it was less than 0, you did not have any x-intercepts if you were to graph it. So let's try out 2 examples. So for these 2, we're just trying to determine the number of times the following functions intersect. And we're not going to solve because that's a waste of time. And if you ever see that it says without solving, that just means without actually factoring or using quadratic formula. Using the discriminant is not solving. So first thing we want to do is still set it up as if we're solving. So I'm going to set x squared plus 4x minus 5 equal to negative x minus 12. And I'm going to bring everything over. You have to pretend you're about to solve to use the discriminant. So I have x squared, and then I'm going to have plus 5x, and then negative 5 plus 12, which is positive 7. And now instead of wasting my time trying to factor or do the full quadratic formula, I'm just going to go to my discriminant. So b squared means 5 squared minus 4. The a value is 1 and the c value is 7. And when I simplify that, I end up with negative 3 for my discriminant. So that means the discriminant is less than 0, which means you'd be trying to square root of a negative number, which you can't do. So therefore, there are no real solutions or points of intersection, because we are talking about how many times the functions intersect. And now I want you to try the next one on your own. So set up your system, bring everything to one side, do the discriminant, and then come to your own conclusion. So pause the video and try it out. All right, so when you set your equations equal to each other and bring everything over, you should have 2x squared minus 5x plus 2. If you messed up there, you probably forgot to switch a sign. When you do your discriminant, make sure the negative 5 is in brackets to the power of 2, so that when you actually simplify, it's going to be positive 25, subtract the 16 to get 9. So because my discriminant is positive and it's greater than 0, that means I have 2 real solutions or 2 points of intersection. And that's it. So when you have a line and a parabola, you can solve algebraically for the points of intersection by doing substitution. Or if you just care about the number of solutions, we'll just look at the part of the quadratic formula that's under the square root, and that's called your discriminant.